Okay, so hello and welcome back. So in this video we want to basically do exercise 16.1. I did do these exercises, but then I was then basically very tired in the very beginning of the exercises, so I deleted the video, and then I got into one particular problem. And the problem is that it's not really easy to calculate the to write the sample space of some particular experiments. I'll tell you what basically that is, and then hopefully we will find a way to do that. It needs some sort of a specific algorithm, and you need to find that algorithm. Well, we do need to find the algorithm on our own, because I'm sure the algorithm does exist, probably in computer science or somewhere like something like that, because this is, I mean, most probably the kind of thing that is all the time done by computers or something, or in different programs in different situations. But I don't know. I mean, I don't have any name for the algorithm, so I cannot look for it, and so I have to come up with the algorithm on my own. Now, for example, let's start with the exercises. I'll tell you what exactly I mean. So it says that in each of the following exercises 1 to 7, describe the sample space for the indicated experiment. So you want to describe the sample space for the indicated experiment. Let me come over here and then take a look at the okay, so I want to have access to the solutions here. Class 11 mathematics. Go chapter 11, probability 16.1, download. Okay. So now the first exercise that we have, that exercise number 1, is a coin is tossed 3 times. Now you need to pay attention to how these go, and then if you are lucky, it must not be that complicated to find the algorithm. So a coin is tossed, for example, a coin is tossed 3 times. Now, if a coin is tossed 3 times, that means that you have a first time, you have a second time, and you have a third time. And, well, the first time you could get heads or tails, the second time you could get heads or tails, the third time you could get heads or tails. There is no other possibility. Now, the sample space for this experiment would therefore be basically the S could be described as all the ordered pairs x and x comma y, such that x x comma y comma z, because we have actually we tossed the coin 3 times. So you have let's just write it as x comma y comma z, such that x basically is related to the first time, x is related to the first time, y to the second time, to the second, and z to the third. to the third. So you could describe the not the namespace, but the sample space for this experiment as this. So you have these three triplets, and so your triplets would be, now it's important, originally I came up with a way to do this. Now let's see if I can get that again. So what I did in basically the first time that I did these was that basically you write H and H and H, meaning that I take this H and this H and this H. And then over here, the way that I understand it myself, the way that I think I'm doing it, is that I take this last choice over here and switch these. So that means that I get H, T, right? And then once I switch this, then I have already switched this, so I have to go back and switch here. That's how I think I'm doing it. Although the explanation does not work when it gets more complicated. So let's see how that goes. So then the third time, or the third element here would be, basically I take this as, instead of the H over here, I want to switch this one. So I write over here H, and now I have already done H over here. I have already done HH, HT, HHH, and HHT. So I want to switch here. So I go for HT, and then I get basically one either heads or tails here, or I go for HT, and then I get either heads or tails here. So then I can put heads here and tails here, and that would be also taken care of, right? Now, what I need to do, the way that I understand it, and the way that it actually works, is that I have to do the same thing over here. Meaning that this time I go with T, and then basically start with T here. So I go with T, for example, and I start with an H, and start with an H. And then I switch these two. So I'll get TH, THH, and THT. So THT. And then I switch these two, meaning that I get basically, so I get basically, since I have already done H, so I'm left with T here. So I get T, 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 H, and I get T, T, H, and T, T, T. And that seems to be all the different outcomes of this experiment, which is of course 2 raised to the power 3, which is equal to 8. So you need to find 8 elements over here, right? That's the number of times that you do the experiment. That's the number of times you do the experiment. And that is basically the number of the possible outcomes of each time you do the experiment. The total number of outcomes each time each time you do the experiment. Now I do not really know why this works. This must be basically based on some concept, like for example combination or permutation or something like that. I do not know based on what that is, but it works. We will go with it for now, and we will figure out what that is later. So that's how I can basically do this simple case. So with this we have no problem. Now the second question is, a dice is thrown 2 times. So a dice is thrown 2 times. 2 times. So if a dice is thrown 2 times, so what happens is that the first time, so over here we said that basically the total number of outcomes each time you do the experiment becomes the base here, and then you raise that base to some power which is the number of times you do the experiment. So since the dice is thrown 2 times, so this would be 6 raised to the power 2, which is equal to 6 times 6, which is equal to 36. So that means that for this experiment, I actually should get 36 elements, which is right, okay? Which is not wrong, which is right. So what I need to do here is maybe a table would also be helpful, not to get confused. But then when we have more than 2 outcomes each time, then we need to make the table 3-dimensional, which is not easy to do, at least on paper. So let's see how it goes. So if a dice is thrown 2 times, so basically what happens is that basically you throw your dice 2 times, and basically you have the first time, right? So you have the first time and you have the second time that you throw your dice. And so for the first time you could have either 1 or 2 or 3 or 5 or 4 or 5 or 6. The same outcomes you could have the second time, 1, 2, 3, 4, 5 or 6. Now this is easy, this is not complicated. Because you could take, for example, 1 with each of these numbers, 2 with each of these numbers, 3 with each of these numbers, and so on and so forth, and go all the way to 6 with each of these numbers. So your sample space would be S, for example, 1, 1, and then you would have 1, 2. Now suppose that, for example, you do this experiment 3 times in a row. You would have 6 over there, 6 over there, and 6 over there, meaning that you would take, for example, 1 with 1, and then with one of those, for example, one of those ones over here, meaning that you would get some construction like this. You would have a cube. It would have to be 3-dimensional. Otherwise you couldn't do it. I mean, that's the model that I think would work in the case of such things. Meaning that, for example, in the case of, in case where you basically do the experiment 2 times, Of course, this two-dimensional model does work, meaning that you can get basically this kind of table over here, and you could have 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, and 6, and then basically wherever these two basically meet, this would be 1, 1. This would be, for example, 1, 2. This would be 1, 3, and so on and so forth. This would be 2, 1. This would be 2, 2. This would be 2, 3, and so on and so forth. And over here you would get to 6, 6. So this is the two-dimensional model that works for this particular situation. Now, if you did this experiment, for example, if you throw the dice 3 times, then you would need another dimension here, meaning something like a z-axis, or for example like an x-axis. You would need some other dimension here. So this would be, for example, your x-axis, this would be your y-axis, and this would be your z-axis. And along this axis you would need again the same thing: 1, 2, 3, 4, 5, and 6. And then over here you would have a basically over here you would have a, for example, you would have a this would be your 1, for example, and so that would be 1, 1, and for example, and this is 1 as well. So you would get a 1, 1, 1 here. And then basically again over here you would get a so along this axis you would have a 1, along this axis you would have a 1, along this axis you would have a 2, so that would be 1, 1, 2, and then again 1, 1, 3, and so on and so forth. And then over here you would get 6, 6, 6, 6, 6, for example. So that would be the three-dimensional model that would work in this case. So now let's first do this one over here, and then we will worry about the rest of the exercises. Okay, so now let's take care of this dice problem. So the dice has been thrown two times, and so you get all of these basically results as, or elements as 1, 1, 1, 2, 1, 3, all the way up to, for example, 1, 6, and then you will get, for example, 2, 1, you'll get 2, 2, all the way up to, for example, 2, 6, 3, 1, for example, all the way up to 3, 6, and you can go all the way up to 6, 6. That is your basically your sample space. Now, if your sample space is that, and they have basically defined the sample space as basic as all the ordered pairs x, y, such that x and y is equal to 1, 2, 3, 4, 5, and 6. They have defined it this way, meaning that if you see this thing, what it means is basically is this thing over here, and therefore you can basically write the same thing to mean the same thing as well, although it doesn't make, I would basically explain a little bit more, but well, since everybody understands it, so there is no problem with that. So now, basically, question number 3 is a coin is tossed 4 times. Now, this is a little bit. This was a coin. Number 2 was a coin. The dice is thrown 2 times, and a coin is tossed 3 times. So we already solved the problem of the coin having been tossed 3 times. Now the coin is tossed 4 times. Now this gets a little bit more complicated. So let's see how we can solve this one. $440. So now if a coin is tossed 4 times, a coin is tossed 4 times. Now if the coin is tossed 4 times, on the first throw you will get either heads or tails. Second throw you'll get either heads or tails. And this is third throw, you will get either heads or tails. And fourth throw you will get either heads or tails. So now you will need to find a way to So what I can do is that I can take the results of. Okay, so now in order to solve this problem, I don't know where exactly I was, but I'm going to start over. So you see, to solve this problem where basically the coin is tossed 4 times, you already had the problem that the coin was tossed, for example, 2 times. When the coin was tossed 2 times, what we had was basically the first time you could get a heads and tails. The second time you could get heads and tails, and then each of these options has to be now if you basically pay attention to what we did in order to get all the different 4 basically possibilities of these 2 basically put together, we took H with H, meaning H and H heads tails, and then you have to do the same thing with tails as well. Takes tails with this one and also with this one. That means that you take tails with heads and then you take tails with tails, and that gives you all the different possibilities of basically 2 pairs of heads and tails combined together in this manner. So now this is easy, and of course this you can do without any problems, but it gets complicated when it comes to, for example, 4 times, basically a coin tossed 4 times, and that's basically there it gets basically a little bit complicated, and well, to be frank with you, I have been thinking about this problem for a few hours now. Of course, I've been doing different things, going different places, walking and so on and so forth. But the only thing that I did during the past few hours was just thinking about this problem to come up with some sort of solution to solve this problem, because you get into trouble if you want to solve this problem. And let me show you the kind of trouble that you can get into. So for example, if you were to solve this problem based on the algorithm that we developed in the previous examples, we said that we could start with H, and H, and then you have to switch the last one. meaning that you need to switch this one to, for example, and switch this one, and you will get a HHHT, right? So now you have basically these three H's with an H or with a T. So that there you have no problem. Now what you need to do, since you have done the switching here, then you need to go back over here and switch this one, meaning that I need to go in and write HHH, and instead of H, since I have already once written H, for the third one I will write H, and then instead of H I write a T, and then again H, T, and then I have to basically I have to consider this with the two different possibilities of this two, meaning that then you could get an H over here or a T over here. So again you would get these two as well, right? So I switch this one and keep it at some, for example, I switch this one and keep it at T, meaning that T does not change here, but then after T has to be considered with every possibility of these two basically right here, because these come after the third one. And then so once this round is complete, then you need to go back and switch this one, meaning that I will write H instead of H this time. I write T, and then the problem is that I need to basically switch this one, but then meaning that I write H over HT over here, right? And then I need to consider these two with every possibility that I get in the remaining two placeholders, meaning that over here I could get either an H or a T, and here I would get either an H or a T. And so this gives me basically, so this could change. For example, I could take HT, HH, and TT and TH, right? So you see, you get basically two things over here. Based on this, you would get, based on this one, you would get, for example, HT, for example, TT, TH, TT, and then after that you get TH. You get TH with HT unchanged, and so TT and TH and HT and HH. So you get again HT unchanged, and then you get HT, HT, HH. Seems that I actually found some way to do it, but it's not actually the best way to do it. So that means that basically now I don't have to repeat this one, and so these are the different the four ones that you get over here, and then I have to basically change this one, meaning that I have to switch this one to T. The first one I switch to T, and then after that again I have to switch these two, meaning that each of those can be either an H or a T, either an H or a T, either an H or a T. So then I can go in and, for example, choose for example HTT, HTH, HHT, HHH, and do the same thing again, back and forth, and I will get another 1, 2, 3, 4, 5, 6, 7, another 8 different possibilities, which is actually mathematically pretty interesting. So then what I can do is that let me use colors. So I go for example, HT. I go for HT and then T and H here. Then the next thing that I can do is I can go for HH and then these two here, and then I can do the same thing with T, right? So let's first write the first four, and then we will think about the rest of them. So that is T, for example, HTT, HTT, and then T, HTH, THTH, and then you have T, HHT. So you have T, HHT, and then HHH, HHH. So T, HHH, and then you will have basically, erase this and do the same thing for T. So now you can go in and go for example, T, and TH, and then you can do the same thing here, basically TH, and then do the same thing here, right? So that gives you basically TT, and TTT, and so this remains sorry. So TT, so that gives you TTT, so T, and then another TTT, so 4 T's, and then T, TTH, TTH. So that means that this, and then you have another T, and then T, HT, and HH. So TT, HT, and TT, HH. So you see that in this manner you will get 16 different possibilities for these coins basically tossed together, right? Now this could be a little bit confusing, especially if you don't know if you don't know how to set this thing up, and I set this up, to be frank, by accident. I couldn't do this until now, and instead of this I came up with something else which I think might work. So let's try that one. You see, what I have over here is basically a coin which has been tossed 4 times. So I think what I can also do to do the same thing is that I'm going to get basically a coin that has been tossed 2 times. So the first time and the second time, and then again I record my results over here, and then again I take the same coin and toss it for the first time and the second time, and I'll show you what I mean by this. So the first time and the second time. So now, since the first time I could get an H, a T, an H, a T, an H, a T, and an H, a T. So this is easy. This is I can simply write this as, for example, HH, HT, for example, TH, and TT. That I can do. So these are basically the 4 different possible results over here. And if I toss it another 2 times but separately, I would get the same thing. So HH, HT, TH, and TT. And then what you need to do is that basically now consider each of these separately with each of these different with each of these different possibilities, meaning that you take this one with this one, this one with this one, this one with this one, and this one with this one. The next round you go for this one, you consider that with this one, you consider it with this one, and with this one. Then you can do the same thing with the third one, consider it with this one, with this one, with this one, and with this one. And you can do the same thing with the last one, meaning that you consider it with this one, with this one, with this one, and with this one. So as you can see, you have four basically options here, and each of these options is multiplied, is being taken with another 4. You see 1, 2, 3, 4, 1, 2, 3, 4, and 1, 2, 3, 4. That means that 4 times 4 is equal to 16, which is the number of basically different things that you got over here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So I think this will work as well. So now let me actually write this over here, and then we can actually compare and see what if this basically algorithm works as well. So this is, for example, HHHH, meaning that take this one with the first one, the second one, the third one, the fourth one. So this would be HHHH, and then you have HHHT, HHHT, and then you have HHTH, HHTH, and then you have HHTT, HHTT, and then you have then this one over here. So HTHH, HTHH, then you have HTHT, HTHT, then you have HTTH, HTTH, and then you have HTTT, then you have HTTT, then you have THHH, THHH, then you have THHT, THHT, THTH, THTH, and then you have THTT, THTT, and then the last one would be TTHH, TTHH, TTHT, TTHT, TTTH, TTTH, and TTTT, and TTTT. And I think if we compare these with what we've gotten over here, we will actually, so HHHH is this one, HHHT is this one, HHTH is this one, so we came all the way up to here. HHTT is this one, HTHH is and actually we don't have that's actually valid. HTHH, HTHH, but actually one of these has to be that one. One of these has to be that one. We have made a mistake here actually. So this is HT, for example, HH. Let's take that as that. HTHT would be this one, HTTH would be this one, and HTTT would be this one, HTTT would be this one, and then you have T triple H, which is this one, and then you have T double HT, which is this one, THTH is this one, THTT is this one, and TTHH is this one, and then TTHT is this one, TTHT is this one, and then TTTH is this one, and then T 4 times would be this one. So it does work. You don't really need to do much here. Just flip the coin twice and then put the results together. You will get the results of a coin which has been flipped 4 times, right? So that's basically number 3, which is a coin is tossed 4 times. A coin is tossed 4 times, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. That was number 3. Okay. So the next question that we have is a coin is tossed and a dice is thrown. So this kind of question is also something you can do. So a coin is tossed and the dice is thrown. So if you toss a coin, you will get either heads or tails. And if you throw a dice, you will get either a 1, a 2, 3, 4, 5, and 6. So that means that you can take, for example, H with 1, H with 2, H with 3. So you would get, for example, H1, H2, H2, H3, H4, H5, and H6. Or you could get T1. You could get T1, T2, T3, T4, T5, and T6. So that is your sample space related to this experiment. I think, let me see if the answer is right. So H1 through H6 and T1 through T6. So the next question is a coin is tossed and then a dice is rolled only in case a head is shown on the coin. So a coin is tossed, and a dice is rolled, only in case a head is shown, only in case you get a head, or only in case you get heads. So that means that basically if you get basically when you toss a coin, you will get either heads or tails. So if you get a head, then you throw a dice as well. So if you throw a dice, you will get 1, 2, 3, 4, 5, and 6, any of these. So you would get H1, for example, H2, H3, H4, H5, and H6, and then if you get tails, then nothing happens. So that would be your sample space. Okay, so the next question is 2 boys and 2 girls are in room 10 and 1 boy and 3 girls in room X and Y. Specify the sample space for the experiment in which a room is selected and then a person. So you have 2 boys, 2 girls are in room, 2 boys and 2 girls are in room X, and 1 boy and 3 girls are in room Y. Now specify sample space for the experiment. The sample space for the experiment. So now you want to create a sample space for the experiment. In which a room is selected and then a person. In which a room is selected and then a person. So for the experiment where a room is selected and then a person, so basically I can call these, for example, you have 2 boys here. I can call them, for example, denote them by B, and these girls I can denote by G. And I can call this, for example, B1 and B2. I can call this G1 and, for example, G2. And then these girls I can call them, for example, G3 through basically G3, G4, G5, and this boy I can call it B3, for example, something like that. And so then I can write, for example, room X. So a room is selected, so you have the room, and then, for example, you have XB1, for example, you have, for example, XB2, you have, for example, XG1, you have XG2, you have, for example, YB3, for example, YB3. I don't know if the way that I'm doing it is right or not. Let's see. Y, for example, G3, YG3, and then you have YG4, and then you have YG5. And so that would be your sample space. Let's see if that's the way to do it. Number 6. So for example, you can go for XB1, XB2, XG1, G2, YB3, exactly right. Okay. Now question number 7 is a dice. 1 dice of red color, 1 of white color, and 1 of blue color are placed in a bag. 1 dice is selected as random and rolled. Its color and the number on its uppermost face is noted. Describe the sample space. So you have basically, you have 3 dice. You have 3 dice. You have a red dice. You have a red dice. You have a white dice. You have a white dice. And you have a blue dice. You have a blue dice. They are basically placed in a bag, and then the dice is selected at random and rolled. its color and the number and its uppermost face is noted, and you want to describe the sample space. So now, since you're picking the dice at random, so what that means is that it's possible that you could get the red dice. So the red dice, I call it, for example, I denote that with R, and this with W, and this with B, for example. Then you could get, and when you roll it, you could get 1 through 6. So that would be R1, for example, R2, R3, R4, R5, and R6. And then you could get also W1, W2, W3, W4, W5, and W6. And then you could get B1, B2, B3, B4, B5, and B6. And that would be the sample space of this experiment. So question number 7 is, yes, exactly right. Now question number 8 is, an experiment consists of recording boy-girl composition of families with 2 children. What is the sample space if you are interested in knowing whether it's a boy or girl in the order of their births? And what is the sample space if you're interested in the number of girls in the family? So an experiment consists of recording boy-girl composition of families with 2 children. I don't understand the question. What's the sample space if you are interested in knowing whether it's a boy or a girl in the order of their births? So if you have 2 children, I don't understand the question exactly, but if you have 2 children, basically, if I denote a boy with B and a girl with G, then if you have 2 children, then you could have basically B, you could have BG, you could have basically GB, and you could have GG. That's the sample space if you're interested in knowing whether it's a boy or a girl in the order of their births. I suppose so. Number 1, or that is S, the first part of the question. The second part of the question, what is the sample space if we are interested in the number of girls in the family? So for example, you could, I'm in the same sample space, I could write it as, for example, G, I don't know, G0, for example, and then you could go for, for example, you could go for G1, G comma 1, you could go for G comma 2, and you could go for G comma 3. Something like that. I suppose so. So number 8 is, okay, this is correct, and this is, if you're interested in the number of girls in the family, it could be 0, 1, or 2. So they have written this as basically S is equal to 0, 1, and 2, this way. So you don't have to write the G, so you just write the number of the girls in the family. And then question number 9 is, a box contains 1 red and 3 identical white balls. So you have, basically you have in a box you have 1 red ball and 3 identical white balls. identical white balls. White balls. 2 balls are drawn at random in succession without replacement. So 2 balls are drawn at random in succession without replacement. Write the sample space for this experiment. So you could call these, for example, W, and you could call these with, denote them with R. And I don't understand what sort of sample space. So what that means is that, for example, if you go based on the succession without replacement, if I take the red ball, then I will be left with either W1 or W2 or W3. I could pick any of those 3, but let me see how they have solved this problem. So RW, W, RW, W. Okay. So the way that they have solved it is that they have basically what they have written is basically you could basically get the red one and then a white one, and since the whites are identical, so you can denote each one of them with a W. So you don't need W1, 2, or 3. Or basically you might get one of the white ones and then the red one, or you might get 2 white ones. That is your sample space, that is here. Okay, so that's number 9. And number 10, an experiment consists of tossing a coin and then throwing it second time if a head occurs. So an experiment consists of tossing the coin and then throwing it the second time if a head occurs. If a tail occurs on the first toss, then the dice is rolled once. Find the sample space. Oh my god. Okay, so basically the experiment is you toss a coin. So you toss a coin, meaning that when you toss a coin you get either heads or tails, and then you throw it the second time. If basically head occurs, you throw the coin a second time. When you throw the coin, what that means is that again you will get either heads or tails, right? And if tail occurs on the first toss, then a dice is rolled once. Meaning that you get basically either 1 or 2 or 3 or 4 or 5 or 6. And then the same thing keeps happening again, meaning that if you get a head, then you throw then basically again you'll get either heads or tails. If you get tails, then again the same thing happens. Okay. So then in order to write the sample space in such a way that it conveys the meaning here, so what you need to do is that you need to write your sample space as if you get a head, then what happens is that you get either a head or a tail. You get either a head or a tail. And if you get a head again, you will again get a head. Right? So if you get a head, you will again get either a head or a tail. So that then if you get tails, you will get either 1 or 2 or 3 or 4 or 5 or 6. And then here you're supposed to stop, right? Here you're supposed to stop. But here again you keep doing the same thing. Meaning that so let me read this again. So tossing the coin and then throwing it second time if the head occurs. So if you get a head again, you have to toss the coin and you get either head or tails. So how do we write that? Well, I think, believe it or not, that's actually the right sample space for this experiment. But I do not think that this experiment is supposed to be basically done over and over again, meaning that you toss the coin once, and if you get heads, then again you toss the coin or you drop the coin, and then you get either heads or tails, and then if you get tails, then you get either 1, 2, 3, 4, 5 or 6, and that's it. That's the experiment stops. I was assuming that the experiment would keep going on. For example, if you got tails, then you would again basically throw dice, or if you got basically if you got heads, for example, again you would again I don't know, drop the coin again or something like that, but it seems that that's actually not the case. So I will end this video here, and then we will continue in the next video.